question, they told us that alkanes are saturated hydrocarbons, right? They're saturated. Even though you should know this without them actually telling you. And this is an example of an alkane. So this is ethane, it has 2 carbons, and it's saturated, meaning that all the bonds are taken up. And here we have an alkene. An example is ethene that I've chose. And basically there's a double bond here. It's unsaturated because, well, not all the bonds are used up. So what can alkanes actually undergo? And in this case, they don't undergo addition reactions. So if you've seen the previous video, you've noticed that we were adding bromine to that alkene. And you know, this double bond can break and then you can form bonds here, right? So this will break and you can form 2 more bonds here. However, you can't really do that with an ethane or an alkane, basically. So that's why options A and D are out. A and D are canceled out. Now, alkanes can go through substitution reactions, like you can substitute an H with a Br, for example. But however, electrophilic substitution is something that alkenes or alkynes go through. So electrophilic substitution involves electrophiles. And electrophiles are basically electron-loving molecules. And then you know that the opposite of phile is phobic, or so phobic, coming from the word phobia, which means fear. So you might think of example hydrophilic or hydrophobic, and these words should be familiar to you, especially if you take biology. And so that's essentially what it is. So it's molecules that love electrons. We look at this alkene, for example, it has this double bond, and when there's a double bond, there is a sigma bond and a pi bond. And pi bonds look like this, right? They go over the actual bond. And this is basically where we can imagine where the electrons can be found. And there's this like huge density of electrons, right? And so if an electrophile, or just whatever molecule this is, I'm just gonna say it's X, right? It's going to go towards it because it's just loving all this electron. However, with alkanes, that's not the case. So B is out, we don't have electrophilic substitution. However, we do have free radical substitution. And free radical substitution is a 3-step process and involves, well, the first step being initiation. Then we have propagation. Propagation can take as many steps as possible. It doesn't have to necessarily just be 1 step. And the final step being termination. So this is free radical substitution. And I'll show you an example. So we have methane, right? And it reacts with, say, a molecule of bromine in the presence of light. So that's the condition that's needed. So you need some UV light in order for this to occur. So you'll end up, I'm going to skip the propagation step. So what it involves, because I don't want to go into too much detail about it, because this question really isn't asking us about the mechanism of free radical substitution. So you'll end up with, as the final step, with this, right? But free radical substitution is basically when it just kind of like breaks in half, and then the electron goes with the bromine, so it becomes like this, and the other one's like that as well. And yeah, that's the free radical substitution, but we don't want to go into too much detail about it right now. If you want to see a full video on it, I'll just let me know. So now that A, D, and B are eliminated, we know that C is the answer. Okay, so alkenes can react with hot concentrate acidified potassium manganate. And basically when something is aqueous, it means that it's in water, so that means there's H plus and hydroxide ions present. Now the answer is D, and I'll show you why. So this is what D is. This is the alkene that ends up forming this. So when we use hot concentrated acidified potassium manganate, it breaks the double bond like that, and you end up getting oxygens where those double bonds were, right? and then we just continue it. Right? So it becomes something like this. But this is the skeletal formula, and it's always easier to use the structural formula, especially when you're first starting out. So I'm just going to place carbons in every little corner, right? So it's going to look something like this. So carbon, the double bond, and then the double bond here again, carbon, and then there's a carbon here as well. So that's another carbon. I'm going to just move this up a bit, taking up space. Okay, then we're going to go down. There's a carbon here and one here, and then the final two right here. So this is what it looks like. However, we all know that carbon forms 4 bonds, right? So this one has 3. So we know that it's missing something. And it says that it's hot concentrated. So that means you'll end up with an OH here to fill up the spot. Here there's 4 bonds, 1, 2, 3, 4, so this one's fine. Here the other bonds would be hydrogen. Now how do we go from this to this? Well, first of all, it actually opens up. So if you open this up, you end up forming this. You have your carboxylic acid on the end. You have your aldehyde, your ketone right here on the second carbon. So you have 1 carbon here, the second one, right? So that's the first, that's the second. So all you have to do is flip it, and then you'll end up with this answer. So D is your final answer. Alright, so for this question, we're talking about tertiary bromoalkane. So tertiary means that the bromine is attached to a carbon that's attached to 3 other carbons. And it's just an alkane because we don't know how many carbons there are. There could be multiple, right? But we don't know, and it doesn't really matter. We need to know that it is a tertiary bromoalkane. So now when we have these tertiary ones, so I'll give you an example. It could look something like this. This is the most basic one, right? They go through an SN1 mechanism, right, when they're reacting. And this is essentially a nucleophilic substitution. So this stands for, so the N is nucleophilic, S is substitution, and 1 stands for molecular. So uni means 1, right? So there's 1 molecule reacting at a time. So that means that there's more than 1 step. That's how you know that there is more than 1 step with an SN1 mechanism. Alright, so that's why you end up with this graph with 2 bumps, right? So this area right here is your activation energy, the energy needed to start the first step. So this is the second activation energy in order to start the second step. So there's a slow step and a fast step, but we do know that there's 2 steps, and I'm not going to go into detail as to not waste time, but there are numerous videos on it, and if you want I can also make a video on it. But in general, you have your reactants here. This is the energy needed for the first step. Yeah, you end up with the first product here, which ends up also reacting again. This is the energy it needs to get you the products or the final product that you're looking for. So C would be your answer because you'll end up with a carbocation. So if you continue with my example, right, there's going to be a positive right here because the bromine is gone now, and we're trying to substitute an OH or hydroxide ion, right? We're trying to substitute it. But anyways, that would end up being C. So, B and D are out because those ones are for the SN2 mechanism, which involves only 1 step. But we're talking about the SN1 mechanism. So here they're saying this is X and this is Y. So Y is where you end up getting that middle product, which is your carbocation or your intermediate products. Okay, so for question 24, again, we're dealing with a nucleophilic substitution. So this is an SN2 mechanism because carbon is only connected to 1 more carbon, so it's a primary halogenoalkane. So this is the process. So the bromine is more electronegative than carbon. So you're going to have a delta negative charge and a delta positive charge. So it's going to move somewhere like this. And then an OH that's wandering around is going to get attracted because it's negative to the carbon, right? So this is what it looks like, right? This is the intermediate. This is the part that we've seen in question 23. And then once it's done with this and the bromine exits, you end up with this final product. Now, bromoethane hydrolyzes more rapidly because it has, first of all, more electrons. So the shielding effect between the electrons in its shell is greater, right? So we have the shell, right? There's more electrons, so there's the shielding, and you know how like charges repel, so it's just pushing it away. That means, so the attraction between the nucleus, the positively charged nucleus, and the electron, the outermost electron, is weaker, and so there's less energy that's needed in order to break this bond between the carbon and the bromine as compared to the carbon and the chlorine. So that is why B is your answer. So in this question, they told us that alcohol X is oxidized to form compound Y, and this is the composition of compound Y. So 54.4% carbon, 36.36% oxygen, and 9.10 hydrogen. And if you add it all up, it gives you 100%. So you can just change that percent into grams, and there you go, that's the mass. So we have the mass. Now we're going to divide it by smaller mass. So carbon, you're going to divide it by 12. Oxygen, you're going to divide it by 16. And hydrogen, you're going to divide by 1. You'll end up with this. And you notice, like I've mentioned before, that the number of moles is mass over molar mass. So mass divided by molar mass. And we end up with this. Now we don't want all these decimals, we want whole numbers. So we're going to divide by the smallest, which is 2.2725, the whole thing, right? So then we'll end up with 2, 1, and 4. So it's carbon 2, oxygen 1, and hydrogen 4. Now if we add this all up, its MR is 44. So 12 times 2 plus 16 plus 4. But they told us that the molar mass of Y is 88. That means you have to multiply the whole thing by 2 because 88 divided by 44 is 2. So you take this whole thing multiplied by 2. So this is basically the empirical formula, but the molecular formula is going to be C4O2 and then H8. So it's going to look something like this. 4 carbons, right? 2 oxygens, OH, and then the rest are all hydrogen, because we know that carbon forms 4 bonds. Now, why it's an alcohol, a carboxylic acid, because a primary alcohol, so a primary alcohol is the same thing where a carbon is just attached to one other carbon, can give you an aldehyde when it's oxidized, and when it's further oxidized, it can give you a carboxylic acid. And then a secondary alcohol, once it's oxidized, it ends up giving you a ketone, and then tertiary alcohols just don't get oxidized. So we can end up with this at the end. And aldehydes only have 1 oxygen, but carboxylic acids end up with 2. So that's why I ended up drawing this. And your final answer is C. All right, so we have this compound, compound Z. And I'm just going to name the following functional groups. So we know that this is an alkene here. Here we have an aldehyde. And this one's a ketone. Aldehydes are always found at the end of the structure, and ketones are in the middle, or basically just not the ends. So it reacts with sodium tetrahydroborate, and basically that's a reducing agent, so it's going to reduce the aldehydes and ketones. So like I've mentioned in the previous question, alcohol, a primary alcohol when oxidized gives you an aldehyde, and a secondary alcohol when oxidized, it gives you a ketone. So if we want to go back to the alcohol, we have to reduce it, so we're using a reducing agent. So it goes back to the primary alcohol and the secondary alcohol, and so A is your final answer. Okay, so in this question, we're trying to identify compound Q. They told us that an orange precipitate is formed when they add 2,4-DNPH, which is dinitrophenylhydrazine. And this essentially tests for aldehydes and ketones, so basically carbonyl groups, compounds that include a carbon that's double bonded to an oxygen, but not carboxylic acid. So, because that would be a carboxyl group, so, but in this case, this is a carbonyl group. This valence reagent is originally blue, and then if there's an aldehyde present, it's going to change to a red-brown precipitate. So we know that there's an aldehyde for sure, and that's the compound is an aldehyde. Now, a pale yellow precipitate forms with alkaline aqueous iodine, and while alkaline aqueous iodine tests for methyl ketones. So basically, a methyl ketone is something like this, as an example. This is an example of methyl ketone. So you have this methyl group and you have a ketone here, but it's, well, another name for this one would end up being ethanol, which is an aldehyde, right? We could have just expanded it and had like an H here, right? That's a methyl group, a ketone, and then more carbons. So this, in this case, is still considered a methyl ketone. However, it is no longer an aldehyde. So in this case, this is just ethanol, right? This is just an exception where the only option that gives us this is A. Okay, so we're trying to find out what happens when sodium hydroxide or aqueous sodium hydroxide is added to separate samples of tartaric acid and J. So this is tartaric acid, and they said to form J, it reacts with this compound here, which is a reducing agent. So we have these carboxylic acids right here. Those will end up getting reduced to an alcohol, and then the alcohols will just stay the same, right? So these will get reduced and you'll end up with an OH only. So this is J, right? Now when we're adding sodium hydroxide, now sodium hydroxide is a base, right? Carboxylic acid is a weak acid, but it's still an acid. Carboxylic acid is a weak acid and sodium hydroxide is a base, and they can react, which is an acid-base reaction. However, here we only have alcohols. Compound J just has hydroxyl groups, so OH. And you can't have a base react with a base, so only tartaric acid would react, so B is your answer. Okay, so we have this compound here, and it reacts with concentrated sulfuric acid. And this is what it looks like drawn out. And you've noticed that there's a carboxylic acid and an alcohol. So they'll actually react. That's why we end up with this cyclic compound, and you'll end up with an ester, and this is called esterification. So the compound would end up looking something like this. We have here C double bond C, C here, double bond O, O, carbon, and carbon. So 1, 2, 3, 4, 1, 2, 3, 4. So this is what essentially it looks like, and that's option C. It looks just like it, it's just moved around. So I can flip it, I can start this here. So you have your double bond here. They decided to have the carboxylic on this acid. So this is the carboxylic end, right? This end is the carboxylic side, and this is the alcohol part. And when esterification happens, you end up getting rid of the OH and H to form H2O, and then these end up bonding together. So removing water is sort of like a dehydration reaction, and then these end up bonding. Now for question 30, and the last question for this video, the answer would be propan-2-ol, which is D. Because if you look at your infrared spectrum, of course you're going to be using your formula sheet, and that actually has the values that you need. So there are little dips, right, or absorptions, and it ends up being absorbed in the alcohol range. So if you check, I'll paste a picture for you to see, and you notice that there's a little, there's a dip at that alcohol range. And you know, in the formula sheet, there's the H bonded alcohol and the free alcohol. And at first I did not know the difference. However, this website explained what the difference is. And that is it for this video. I hope you guys enjoyed it, and I'll see you next time.